Hi folks, welcome to the fourth lecture of the series in this course. Before I begin this lecture, I would like to talk to you what I missed in the last lecture. And that is, I was talking about the name given to electrical insulation as dielectrics. And it's very interesting that, for example, we have an IEEE society which is named Dielectric and Electrical Insulation Society, DEIS. So one would question why both the names have been kept when dielectrics are nothing but electrical insulation, but both the names are contribute for the society. I'll tell you. As I mentioned in the last lecture, dielectric literally means dielectric, something which does not allow passage of current. Initially, when the name was given to electrical insulation as dielectric, say about 150 years back, there were no instruments which could detect very small magnitude of current, microcurrent and maybe millicurrent. So people thought that electrical insulation does not conduct any electricity at all. But as I mentioned, all electricity do conduct some amount of electricity, and since the capacitor is formed by electrical insulation, you know that every capacitor has some charging current. Later, with the time, the detection of very small current was possible. So, electrical insulation was being used more appropriately. But dielectric was also continued for a very long time. And that is why people don't want to give it up for the expression. So that is the reason I wanted to elaborate before beginning the fourth lecture. The fourth lecture just a minute. Yeah. The objective of this chapter, in fact, we are beginning a new chapter, that is the performance of dielectric over its lifespan. Objective of the chapter is the electric field and electric field strength, which is also known as electric stress. We talked about it. Definition of electric fields, classification of electric fields, and utilization factor of electric fields. So these are the topics we will be covering. Let's begin with electric fields. Electric field is one and the foremost thing about electric fields. You must know that the electric fields exist only in insulating materials. There is no electric field in conductors. Conductors have potential which forms electric field around it, and around the conductor, obviously, there has to be an insulation. So the electric fields exist only in electrical insulation. Electric field intensity, we also call it to be the electric field strength. We can define it as the electrostatic force, mind it, electrostatic force F exerted by the field on a unit positive test charge Q placed at a particular point P in a dielectric. If you change the location of the point or location of putting the unit positive charge, the field intensity may change. Within a dielectric, field intensity may not be constant all throughout. We'll learn about this phenomenon more in detail today. And the electric field intensity is denoted by the symbol E, you must be aware, and E, which is expressed in newtons per coulomb, that is the force per unit charge. Now, the electric field intensity is measured in practical units of volts per meter, or that's a very odd combination. So normally we denote it by kV, kilovolts per millimeter, or kilovolts per centimeter. So electric field intensity is often more specifically mentioned as electric stress, you might have heard, experienced by a dielectric or an electrical insulating material at a given point. Because, as I mentioned, electric stress is not constant all throughout the dielectric produced by a given potential. So the electric stress would matter at different locations of the dielectric. But why do we call it electric stress? Stress, you understand, simple meaning of stress. That means even the human being gets more stressed under certain circumstances. So the dielectric is given a, you can say, physical stress because of electric field intensity. So that is how electric field is also given the name electric stress. Now, when we go back to the history and the people who felt it, described it, Faraday described the space around a magnet to be filled with lines of magnetic force. You all must have learned. Similarly, the region around an electric field object, electrified object, region around an electrified object, that is an object which is having electricity, which the electricity may be static or may not be static, may be considered to be filled with lines of electric force, unlike the like the magnetic force created by the magnet. Because of the electric field, electric force is created, as we also defined it. To Faraday, these lines existed as mechanical structures in the surrounding medium, the dielectric, and could exert force on object placed therein. Yeah, you can see it here. The electric field on the top figure, it's a sphere, and on the bottom it's a ground or a plate. Between a sphere and plane or a plate, you can see the plane, the metallic surface, let it be sphere or the plate, forms equipotential surface always. As I said, there is no electric field intensity in metals. It exists only in the dielectric. So as you can see, between the sphere and the plane, the electric field has been plotted, and of course also above the sphere. And the plane surface here is normally grounded when we apply voltage to the sphere. And electric equipotential lines are in configuration, in more or less parallel with the electrode surfaces. As you can see, these are the equipotential lines here. These are equipotential lines, and then the uh, the fixed the mm, force lines also, we call it charge flow lines, current line. So people put it in different expression. They intersect the equipotential lines at 90 degrees. When you plot this field, you might have plotted before coming to this lecture, you might have been asked in some basic electrical engineering course to plot the electric field around, and the current flow or the charge flow or the uh, you know, what do you, yeah, current flow or charge flow lines, they intersect the equipotential lines at right angle as possible when you draw it. As you can see, these angles are tried to be made at right angle. And as you can see, the squares formed between the two lines, that is equipotential and the flow of charge, these squares work out to be much smaller in this region. Why? Because the electric field intensity is highest over there. The smaller is the square dimension, more is the electric field intensity. In the region away from the main electrode system, for example, here, the squares are much bigger, so the electric field intensity is much smaller. So this is the by thumb rule, you plot these. There are methods of plotting these electric field. You can plot with FEM, earlier electrolytic fluid tank used to be there. Then the fluid was replaced with conducting paper, like that. So there is a long history about plotting these electric field between any two electrodes. The one at the bottom, as you can see, this is the electric field plotted for a bundle conductor. What is a bundle conductor? You might have learned. This is a very common way of having a conductor in a bundle of 4 conductors at the same potential. All these conductors are having the same potential, and this is very commonly used for high voltage transmission lines. And as you can see, how the electric field, when you consider all the 4 bundles together, the electric field density around the bundle conductor is much lower, because you have a much bigger circle around the conductor as compared to the circle around one conductor. So effectively, the bundle conductor, all bundles being at the same potential, act together and increase the effective radius of the conductor tremendously, and that is how the field around the bundle conductors is considered, it works out to be much lower. Yeah, when we have mathematical, see all these things in high voltage engineering, people felt the effect first and then tried to derive it mathematically. So let's try to understand how the field intensity and electric stress, etc., has been derived mathematically. The potential difference between 2 points, let's say A and B, let's consider a point here. We have A and the point here to be B. And let's have this, the electric potential to be phi A, and here phi B. These are the 2 points we are considering in a dielectric. So the potential difference between 2 points A and B having scalar potential in a space charge free electric field, I'll explain, a space charge free electric field is defined as the work done by an external source in moving a unit positive charge from B to A. As you can see, the potential difference here, AB, is defined by the work done in moving a unit positive charge from, in this case, we have taken phi A minus phi B, and that is why a negative sign works out. That is mathematics. So, yeah, I told I'll define space charge free field. What do you mean by space charge? If you're making notes, you can note down that space charge means concentration of like polarity charge. You know the polarity, there are only 2 polarities of the charge, positive or negative. When any one of them, negative or positive, make a concentration, that is called space charge. And in this condition, it is space charge free, means there is no concentration of any one polarity charge. That means the charge, the positive and negative charges are equally distributed in this region, okay? Yeah, UAB is positive if the work is done in carrying the positive charge from B to A. And since it was A to B, it is what works out to be negative. And the maximum magnitude of electric field intensity is therefore, you can explain, you can define, given by the maximum value of the rate of change of potential with distance. It is given by the maximum value of the rate of change of potential with distance. It is obtained when the direction of the increment of distance is opposite to the direction of to the direction of the field intensity E. Here, direction of E, you can note down, direction of E. In other words, the maximum value of the rate of change of potential is obtained when the direction of, again, E is opposite to the direction in which the potential is increasing most rapidly. So, you can say UAB, dUAB by dx, that is the rate of change of potential between 2 points A and B, is maximum of the value of the rate of change of potential is equal to minus E max, and that is how the derivation E is equal to minus gradient of potential. Gradient is the rate of change. So, yeah. Now we come to some forms of electric fields. As you can see here, there are 2 forms of electrodes, 2 extreme forms of electrodes shown here. The one you might have come across in life very often. These are 2 needles. You can say needle electrodes. We call it needle electrodes. And between two needle electrodes, if you give here, this is positive potential and this is negative potential. Obviously, I mean, you're giving bipolar DC potential to these two needles. In the center of the needle, that is in the center of the dielectric, there will be a zero potential, as you can see it here. There will be a zero potential. So this is positive high potential and this is negative high potential. So when you plot the potential or the voltage, you can say, within the gap, as you can see here, that this is beginning here positive potential and equally the negative potential. That is the bipolar plus minus two potentials are distributed this way in the gap, and in the center there is a 0 point. And then that is how the Emax between these two, you will have two maximum or two extremes of the field intensities in this case. So one is positive maximum potential, another one would be the negative maximum potential. This is plotted here in this case in this way, that because these two intensities will be same. The intensity of electric field will be the same at these two locations, that is at the tips of the electrode in the dielectric. So this is an extreme configuration of electric field variation. Let's say, and we call it extremely non-uniform field. We call it also extremely non-uniform field. This two, and we'll have it in the next slides more. Unlike this, we can have, when you plot here, as you can see, once again, when we come back to the needle electrode system, the squares formed between the equipotential and the charge flow lines here are very, very small. In this region, it is very small, and in this region, when you go away from the electrode, the squares become much larger. So there is a vast difference in the field intensities, as I mentioned, at the wherever, when you plot the field, wherever the squares work out to be smaller, the field intensity is high. So at the tip of the electrodes, the field intensities are very high, but in the when you go away from the tip of the electrode, the field intensities reduce considerably. Now, when you take large plane electrodes with a given shape here, as you can see, this shape has been given here. This shape has been given at the brims of the plane surface or plane electrode. Plane electrode normally is considered to be a circular electrode, and the brims of the electrode are extended in this fashion, as I show it here. And when you do that, at least in the central region of the field, the squares would work out to be, they are not very well plotted here, the squares would work out to be perfect square, I can say. They will work out to be perfect squares, and the size of the squares would be uniform. In such a case, the size of the uniform would be size of the squares throughout the space between the two electrodes, the positive here and the negative here, would work out to be of equal size. What does it convey? when the squares work out to be of equal size, means the field intensity all throughout the space between the two electrodes will be uh, same. Between the two electrodes it will be same, and that is how the potential would linearly vary from positive to negative. Here the potential would vary linearly, and the field intensity, as you can see, it is constant in this half positive value, then comes the zero potential line, and then the constant negative value here. That is how uh, the field intensity would vary, and this configuration we call it the uniform field. That is, now you've learned the two extreme configurations of electric field, the total uniform field and extremely non-uniform field. Yeah. We can come back here and go to the classification first. Yeah, we can go to classification of electric fields first. So as we learned just now, the uniform field. This is, you can say, when a uniform field, it has to be created. Anything which is not uniform is given the name non-uniform field. Now you can further classify the non-uniform to be in two ways. You can classify. We learned extremely non-uniform field between the two pointed needle-shaped electrodes, but there is something like in between the uniform and extremely non-uniform fields also. We call it to be the weakly non-uniform field. Now, how do we distinguish between these? There was a need to understand a phenomenon known as partial breakdown. What happens when we go back to this slide? When you increase the voltage between the two electrodes, as soon as we explained, there is a maximum field intensity at the tip of the two electrodes. As soon as the field intensity at the tips increases, some phenomenon will begin there, may not elsewhere in the dielectric. And dielectric may lose its insulating properties locally. There, locally it may lose its insulating property. When the dielectric loses its insulating property locally, not throughout the dielectric between the two electrodes, we call it to be a partial breakdown. Yeah. Where is the other slide? Yeah. Wait a minute. Yeah. So that slide of classification, it was there. Anyway, it disappeared. Yeah, we can classify here also. You see here what happens. This is between two, one pointed electrode and the plane. This is the uniform field between two um, um, plane electrodes when the brims are given shape. Here between needle and plane is the extremely non-uniform field configuration. In between the weakly non-uniform field, as we were talking about, and the weakly non-uniform field configuration, mm, uh, you can see it doesn't have any pointed electrode. It doesn't have electrode system like in uniform field. This is between, you can say, two coaxial. This one is between two coaxial cylinders, concentric cylinders or coaxial cylinders. And the difference is when you increase the voltage, this voltage in extremely non-uniform field, some phenomenon of breakdown will occur at the tip of the electrode because there the field intensity is very, very high. And that we call it to be PB, partial breakdown of the dielectric. In this case, in the case of uniform fields, the field is all throughout the same. So no such phenomenon like partial breakdown will occur because the field intensity is the same all throughout the dielectric. And when you increase the voltage, there will be a breakdown through the dielectric. When you compare the two, the weakly non-uniform configuration is close to the uniform field configuration. That means there also no partial breakdown occurs. When you increase the non-uniformity, here the uniformity is a very highly uniform field in uniform electrode configuration. When you begin or start giving different shape to the electrodes, the non-uniformity begins, but the characteristic of the field remains closer to the uniform, and so long it remains closer to the uniform, we call it weakly non-uniform. And one thing common between the uniform and the weakly non-uniform fields is that partial breakdown do not take place in both these fields, uniform and weakly non-uniform fields, before the complete breakdown. And that is a very important characteristic discovered over the time with experience. Whereas in extremely non-uniform field, there will be first partial breakdown and then complete breakdown would occur in a dielectric. Now let's define the degree of uniformity of electric fields. You can say the degree of uniformity is of fields, we call it Schweiger factor, as you can see, was given in somewhere in 1922 by scientist Schweiger, very well known in high voltage engineering from Germany. And the factor is denoted by eta. And what is eta? Eta is the ratio of maximum mean electric field intensity to maximum field intensity in a dielectric between two electrodes. Whenever you can take any kind of electrode, and in between the two electrodes, there will always be some insulating material, dielectric. And when you, as I said, between the two electrodes, it is not necessary that the field will be uniform. It may vary from place to place. So when you have to determine where is the maximum field intensity, and the mean field intensity is given by the potential applied between the two electrodes divided by the gap distance between the two electrodes. And when you do this, you get the ratio eta. And the eta is always greater than 0, but it is always 1 or less than 1. So the maximum value of eta, as you can see, is 1, and it will always have some very, very small value. So when eta is 1, what do you understand? That means the mean field intensity and maximum field intensities are equal, and that happens only in the uniform field configuration, as we have learned. So for uniform field, the eta factor would be 1, and for extremely non-uniform fields, it could be very small also. And we were bothered about the factor. Yeah, as we can see, when the eta factor is greater than 0.25, you may have a weakly non-uniform field. I mean, it may differ condition to condition, electrode to electrode, but normally we have come to a conclusion when you find out eta factor between for a given field. When the eta factor is greater than 0.25, the characteristic of the field is closer to the uniform field, and that is why it is known as weakly non-uniform field. And in weakly non-uniform fields, no partial breakdown, as in case of uniform field. You can say in uniform field no PB, in weakly non-uniform field also no PB take place, but in this case PB always would take place. That means partial breakdown would always take place before the global breakdown. So that is how you distinguish between the two fields. I mean, you classify the 3 types of fields. And one thing more I would like to convey here, that the uniform field does not exist in practice at all. You may have to do a lot of effort to produce a uniform field between 2 electrodes with a lot of efforts in the laboratory. So this is only for research purpose, for laboratory experimental purpose, uniform field exists. But in practice, it is either weakly non-uniform field or extremely non-uniform field prevail in the power system. Now, again, one thing I would like to at least apprise you what it is. These curves given to the electrode or plane electrode on the sides, as you can see it here. This is called Rogowski profile. Rogowski was a scientist who calculated exact profile or exact shape to be given or to be extended to a given size of plane electrode, so that the field in between is uniform. Obviously, at the brims, the field is not uniform. When you plot, when we have learned the plot here, as you can see, the at the brims here, the squares are not uniform. Squares would be uniform in the center only. So for a given size of the plane, there is a particular curve with which the brims should be extended, and that calculation exists by Rogowski. Yeah, I think, yeah. So now this classification, as we had started with, you can see the mm, the characteristic here. This PUI here is PB inception voltage. So in extremely non-uniform field, in this uniform field, as we can see here, that UI, that is the PB inception voltage, is always much smaller than UB, the breakdown voltage. In both these two cases, uh, this case, uniform field and weakly non-uniform fields, the partial breakdown inception is equal to the complete breakdown voltage. That is the similarity between them. What we learned, I hope things are clear to you. And yeah, when we talk about the electric strength of dielectrics, yeah, that is also a very interesting phenomenon that a qualitative definition of electric strength of a dielectric is the maximum electric stress a dielectric can withstand. This is only qualitative. When you try to find out a quantitative uh, strength, it is very difficult to find out actually. Why? Quantitative. Because a very large number of factors affect the electric breakdown of a dielectric. These could be, for example, in gaseous dielectrics, could be pressure, humidity, temperature. Then, of course, the breakdown strength very highly depends upon the electric field configuration. What is the degree of non-uniformity, that is? We have learned what is the uniformity factor, Schreiber factor. That is determined by the shape of the electrodes, as you have seen. We have taken example of point to point or needle to needle, or the uniform field electrode system, or in case of weakly non-uniform field concentric cylinder system, there could be two spherical electrodes opposite each other, also make a weakly non-uniform field. So besides, under certain conditions, for example, in very high gas pressure or very low gas pressure, that is vacuum, the electrode material also would affect the breakdown strength. Then in practically all dielectrics, the presence of impurities, imperfections in the dielectric, the composition of the dielectric, all these things affect the breakdown strength. Hence, a quantitative definition is very complicated. It must elaborate what is exactly the condition under which the breakdown strength has been measured. You might have learned in some books that some value of breakdown strength is given. That may be for certain ideal conditions, or sometimes it is not described under what conditions it has been measured to be. So don't get moved by the definition simply, if it is simply given, the quantitative definition is simply given without elaborating under what conditions it has been measured. So that is a lot of confusion actually between the quantitative and qualitative definition of the electric strength of a dielectric. Yeah, as I have already mentioned. But when you measure electric strength of an insulating material, you would define it in a time varying AC power frequency field. Very often the breakdown strength is measured with AC power frequency. That is, you can say, we also call AC power frequency voltage to be quasi-stationary field. It is not stationary, it is quasi-stationary. The maximum electric stress always occur at the peak of the applied voltage in case of AC. Obviously, at the peak of the applied voltage, the magnitude of the electric stress or field intensity would be highest, and any dielectric would lose its insulating properties when it is subjected to the highest magnitude. Yeah, there is a definition also about electric strength, what we call it to be intrinsic strength of a dielectric. What do you mean by intrinsic strength of a dielectric? Intrinsic word means inherent, of its own, and it is defined for gaseous dielectrics and for solid dielectrics in a different way. For your information, the gaseous dielectrics have much lower electric strength as compared to liquids and solids. So the intrinsic strength definition has to be made differently for these. For gaseous dielectrics, it is the magnitude of breakdown voltage measured across a gap distance of 1 centimeter in uniform electric field. That means when eta is equal to 1 at normal temperature and pressure. For example, this for air, it works out to be 31 kV per centimeter. You can measure for gaseous dielectrics in a gap distance of 1 centimeter. And the value given for all gaseous dielectrics, intrinsic strength is in, you can say, kV per centimeter. That is the intrinsic strength. There also we will learn later that the breakdown strength magnitude varies with the gap distance between the two electrodes. But for intrinsic strength, the value given is for a gap distance of 1 centimeter in uniform field, and that is something like 31 kV per centimeter in case of air. In today highly used gas, SF6 gas, it works out to be something around 90 kV per centimeter, almost 3 times. And obviously the voltage measured given is always the maximum magnitude of the voltage. If it is DC, there is no question of minimum and maximum magnitude. If it is AC, it is the peak value of the AC voltage. Now for liquid and solid dielectrics, because they have very high dielectric strength, you may require thousands of kV voltage if you take a thickness of 1 centimeter. So it is not possible to measure for a thickness of 1 centimeter of the material in case of liquids and solids. So you take only very thin films, sometimes even micro thin films, to measure the breakdown strength, but obviously in uniform fields. So for liquid and solid dielectrics, it is the highest value of breakdown strength obtained after eliminating all known secondary effects which may influence the breakdown adversely. As I mentioned, there are so many effects which may bring down the breakdown strength. So when you are satisfied that you have eliminated all effects, all secondary effects which may lead to premature breakdown, you can say you have measured the breakdown strength or intrinsic breakdown strength. And if you want to give it for 1 centimeter thickness, since you have measured in uniform field, you can directly convert it to centimeter, whatever may be the actual measuring thickness, actual thickness of the measurement for the dielectric. It is made, as I mentioned, it is written, it is measured for ideal conditions of dielectric in uniform field. Since it is very, very high for solid and liquid dielectrics compared to gaseous dielectrics, it is measured for millimeter and micrometer in thin films of the liquid and solid dielectrics respectively, instead of 1 centimeter gap distance in case of gaseous dielectrics. So that is how the, and of course it can be interpreted into centimeter gap distance because it is in uniform field. Just convert the dimensions. So that is how the intrinsic strengths are defined. So I think we have completed today the first lecture in chapter 2. We'll see you tomorrow again. Thank you.